Okay, so today we're going to be looking at complex numbers in differential equations. Okay, I'll just put DEs, that means differential equations. And then for my electrical engineering friends there, this will be very important for you. Okay, and then the rest of you that are doing physics modules next year, you'll see this as well under equations of motion. Okay, so first thing, why are we interested in this? So complex numbers are used in electrical engineering and physics in general. Okay, to represent phase shifts. Okay, so all of you have covered waves in physics? Yes? No? Okay. You have covered some sort of waves. Okay. So if you have two waves that are offset by some amount, we call that a phase shift. So here, if we have some wave maybe like that, oops, like that, and another one maybe that starts over there, you see there is some shifting between the waves. We call that a phase shift. Okay, phase shift in components. Like capacitors and inductors. And waves in general. Right, your sinusoidal waves. So in terms of capacitors and inductors, we're looking at the current or voltage that has some sinusoidal behavior. Or if you're looking at some wave in general, you have this phase shift between them. Okay, so I'll just put an example for current. So let's say we have some I of t is equal to some amplitude I naught, e to the I omega t times e to the I phi. Okay, so the I naught, that will be the amplitude of the wave. E to the I omega t, we know how to expand that out into sine and cosine. So we can write that as cos omega t. You would have seen that before with your waves, plus I sine omega t. Okay, and we'll look at that in more detail later on, why we include both. And then e to the I phi, that is the phase shift. Okay, so this is a complex version of writing the following: cos omega t plus phi. So you have your angular velocity, your time, and the phase shift. Okay, so instead of writing it like that, we write it in this complex form using Euler's formula. Okay, so that's the first thing, writing it like this. And we'll spend most of the lecture looking at this. Okay. You can use complex numbers. To convert differential equations and integral equations into algebraic equations, which is much easier to work with. Okay, much easier to work with. Okay, for examples, calculations of impedance and frequency response. So again, the electrical engineers, you're going to be seeing that quite a bit. Calculations of impedance and frequency response. Yeah, and then just a note on this impedance. This is a complex value. Okay, given as Z is equal to capital R plus IX. So Z is for impedance. This capital R, that is your resistance. Right, your normal V equals IR resistance. And then X, that is called the reactance. Okay. So we called it Z equals X plus IY or A plus IB. Later on, when you're doing electricity and magnetism in physics, we give special names to that. So this thing called impedance, the real part will be the resistance of whatever circuit component you're working with. And then the imaginary part, that will be the reactance of that circuit component. Okay. So it's exactly the same as what we've been working with, real parts, imaginary parts, but now you're given some special names for it. Okay, but what we're going to be focusing on is the solving differential equations part. Okay, so we're going to be solving second order homogeneous constant coefficient differential equations. So that's the main thing for today. So first, let's do a quick review on second order differential equations that we covered just after that holiday. So let's say we have y double prime plus y is equal to 0. Does anyone remember the two solutions we found for this? Was it? Yeah, cos and sine. Exactly. So we had two solutions. y1 of x was cos x. y2 of x was sine x. And we showed that these were two solutions for a second order differential equation. And we showed that these were linearly independent. And if we have two solutions that are linearly independent, then any solution can be written as some A cos x plus some B sine x. Okay, remember that from last time? Okay. Now notice we've got cos x and sine x. We've got those trig functions. What we want to do is try and combine this into just one solution. So we don't have to remember cos and sine, we just remember one thing. And the way we're going to do that is with Euler's formula, right? Because e to the ix is cos x plus I sine x. So we know that cos x is a solution. We know sine x is a solution. So e to the ix is also a solution. So since cos x and sine x are both solutions, we have e to the ix as another solution. However, if we include e to the ix as a solution, that means that these coefficients a and b are now complex numbers, right? Because a is 1, b is I to get the solution. Okay, so now we need to keep in mind that these a and b's can now be complex. Yeah. So before, we only looked at real values for A and B, right? Initial conditions, we solved for A and B, or we had boundary conditions, we solved for A and B. All of those were real numbers. Now we're going to say, okay, let them be any complex number. Okay, so how does this help us? Well, we know that this e to the ix, where we have this complex number in the top there, is a solution to this differential equation, the specific one here. What we're going to try to do is assume that e to the lambda x, where lambda is some complex number, is also a solution to a y double prime plus b y prime plus c y is equal to 0. Yeah. Again, we had e to the ix was a solution to this very specific one. Okay, very specific one that we picked there. What we're going to assume is that this e to the ix, or in general e to the lambda x, is a solution for any of them. Okay, it's a very big assumption we're making, but we're going to show that it works. So we will show e to the lambda x is a solution to this general differential equation. Okay. For now, this is just a guess. We have no idea if it works or not. All we know is that e to the ix works for what we were given before. Now we hope that this works for what we're given here. So we hope it works. In the general case. Okay. So let's check. So what do we need to check? We're going to take our proposed solution. We still have no idea if it works. We're going to put it into that left-hand side over there. If it matches 0 on the right-hand side, then it is a solution. If it doesn't match, then it is not a solution. Okay, so we need to substitute. So we need y, that's given. Okay. Y prime, we just take the lambda down. And we need y double prime, so we take the lambda down again, so we get lambda squared. Okay. Everyone okay so far? All good. So let's substitute. Okay, so it's going to be a times y double prime plus b times y prime plus c times y. Okay, so we end up with this. Now we've got e to the lambda x for all of those terms, so we can factor that out. Okay, we can just ignore that part and just focus on the first bit, so we can cancel that. So we have a lambda squared plus b lambda plus c is equal to 0. Now, this e to the lambda x is a solution if there are lambda solutions for this equation. Okay, because if this equation works, it means we have a solution. Does everyone understand that? Okay, so the question is, are there solutions to this equation? Yes or no? Yes. It is a quadratic polynomial. We are guaranteed 2 solutions. Right, from right at the beginning, fundamental theorem of algebra, we know that there are always 2 solutions. We know that there are always 2 solutions. We have lambda 1 and lambda 2, guaranteed solutions. Which means we have two possible solutions for e to the lambda x, one with lambda 1, one with lambda 2. So we have this. So all we need to do now, so we've got two solutions because it's second order, that's good. All we need to do now is show that these are linearly independent, and then we're done. We have our two solutions. And that'll be for homework. So homework, finish off the proof, show that these two solutions are linearly independent. Right, you set up your W matrix, take the determinant, and check if it is 0 or not. Show that these two are linearly independent. Okay, it's like 2 lines of working. Just find the determinant and check if it's 0 or not. Okay, once you've done that, that's the end of the proof. We've got two solutions. They're linearly independent solutions. So we have solved the problem. All right. Any questions on this? Okay. So for whatever second order differential equation we get, all we need to do is solve this equation. This is called the characteristic equation. Just make a note of that. So we solve this characteristic equation for lambda. Once we have our lambda, we substitute in and we have our solutions. Okay, very easy stuff. Any questions before we look at the examples? All good. Okay, so let's have a look at some examples. We've got 4 here. We'll see how many we get through. The rest will be for homework. Okay, number 1. We have y double prime minus 6y prime plus 8 is equal to 0. Okay. Now, all we need to do is write down our characteristic equation, solve for the lambda, and we're done. We have our solutions. Okay, so A, that will be a 1. B will be minus 6. C will be 8. So we just have lambda squared minus 6 lambda plus 8 is equal to 0. So now, instead of solving the differential equation, we now solve the algebraic equation, like we said at the beginning. So this is our DE equation. This is our algebraic equation. Okay, so we're skipping all the steps about the differential equation, and we just skip right to the answer after solving this. Okay, how do we factor this? What is it? Yeah, well, what's the answers? Lambda minus 4. Minus 2 or plus 2? You sure? Which one's a plus? The 2. Lambda minus 2. Is that right? Okay. Okay, so we have our two solutions. Lambda, it doesn't matter the order. You can call any of them lambda 1 and 2. So let's say the first one's lambda 1. And lambda 2 will be 2. And we're done. We've got our solutions. So that means y of x will be a e to the lambda 1x plus b e to the lambda 2x. Okay, so we have a e to the lambda 1, so e to the 4x, and b e to the 2x. Okay, that's a 2 there. Okay, so what's this? 1, 2, 3, 4 lines of working. Very easy stuff. Okay, so for homework, go backwards. take the derivative of our solution and show that it works. Okay, just in case we made some mistake. So, homework. Okay, sub into differential equation and check if you get 0. Okay, so it's very easy to check if you made a mistake. You just substitute it back. If you get 0, then everything's fine. If you do not get 0, you have to redo it. You made some mistake. Yes? We don't touch those. We do not touch those. Don't worry. Third order, save that for later years. Okay, don't worry about that. Okay. The issue is first order, easy. We solved all of them. We went through all the methods. Second order, we've covered, Laplace and this. It's doable. Third order, things get quite scary. Okay, so we don't look at that. Probably you won't even see third order your whole degree. Okay. Yeah, when I say they're difficult, I mean difficult. Any other questions? All good. Okay, number 2. We have y double prime plus 4y is equal to 0. So we don't have any y prime, so b will be 0. Okay, but we do have a and we have c. So this will be lambda squared plus just the 4. Okay, because we don't have any y prime. Okay, now we need to solve this. What's the solutions for lambda? Plus minus 2, not quite. Plus minus 2i. Yes, that's right. Lambda plus r times 2, lambda minus r times 2. Yeah. Okay. Remember way back we did the polynomial factoring? That's why, because we have to do it here. Okay. So we have 2 solutions. One with the plus, one with the minus. So lambda 1, let's say that's the one with the plus, so r times 2. And lambda 2, let's say that's the one with the minus. Again, the order doesn't matter as long as you have both. Okay, so we've got our 2 lambdas. Let's write it out. So y of x, that will be a e to the lambda 1x plus b e to the lambda 2x. Then we just substitute. So this will give us a e to the I to x plus b e to the minus r to x. Okay. This form over here, when you leave it in exponential form, this is what you'll have over here. Okay. You'll have it like that in this exponential form. So e to the I omega, that was one of the lambdas for the differential equation. Okay, so you leave it like that later on. But we can also write it in terms of sine and cosine if you want. So let's do both. So what we're going to do is use Euler's formula to write both in terms of sine and cosine. So we're going to have a, and then the first one, that will be cos 2x plus I sine 2x plus b cos 2x minus r sine 2x. Now we can put the cos together. So we have a and b going with the cos. Plus, then we have the ai and the minus bi for this sine. Okay, and remember a and b, they can be complex, right? But this a plus b, we can call that c. And the ia minus rb, we can call that d. Okay, now we have exactly the same solution, but written in terms of sine and cos. Okay, and these are equivalent. So just put a box around this first part. So this is writing it in complex exponential form, and we know that that's the same as this part. Just put a little box around that in trig form. Both are acceptable, whatever you put down, either the exponential or the trig form, that's acceptable. Okay, but notice that the coefficients are now different. Okay, it won't be A and A, B and B. Those are different coefficients. All right, any questions for this one? Easy stuff. Okay, number 3. Y double prime minus 8y prime plus 16y is equal to 0. Okay, so we look at our coefficients. We write down our characteristic equation. Lambda squared minus 8 lambda plus 16 is equal to 0. Okay. So you just take the coefficients down for each of those. Okay, now we need to find the lambda solution. So what do we get? Lambda minus 4. Lambda minus 4. Yeah. And the other one? Yeah, squared. Okay, so I'm going to write that as lambda minus 4, lambda minus 4. Okay, and here we have a slight problem. Okay, because this is a second order differential equation, we need to have 2 solutions. Here we only have 1. So we're going to cheat a little bit and turn this one solution into 2 independent solutions. So we're going to write this as y of x is a e to the lambda 1x plus b, and it's a little cheat or a little trick, however you want to take it. We times it by x. Okay, multiplying by x turns that second solution into another solution. You're going to check that. Okay, so check that that is a solution. And then secondly, check that those two are linearly independent. Okay, so this will be a e to the 4x plus bx e to the 4x. Okay, so homework, 2 parts. Number 1, show that that is a solution, right? I just times by x. I could have messed everything up. So show it's a solution. Okay. It will be a solution, but just to give you some practice. And then number 2, show that those are linearly independent. Right, you take the determinant, check if it's 0 or non-zero. So check if e to the 4x and x e to the 4x are linearly independent. So please check those 2 for homework. Okay. Any questions for this? You're all good. Okay. There's 3. Last one, number 4. We have y double prime minus 3y prime plus 3y is equal to 0. Okay, you see the method is the same for all of them. Just a few things to be aware of for each problem. Okay, we've got our coefficients, 1, minus 3, and 3. So we're going to have lambda squared minus 3 lambda plus 3. Then we need to solve this. What do we get? 5. Sorry? Oh, no, there's no undefined here. We're doing complex numbers. Oh, hold on. lambda 1, 3 over 2. With an R. Okay. Everyone agree? Okay. And then lambda 2. Well, we know what this will be. It's the same thing, both the minus. So as soon as you get the first one, you know the second already. So it will be 3 over 2 minus I root 3 over 2. Again, two solutions, second order. No issues there. Okay. This one's going to look a little bit different to the previous ones because we have a real part and an imaginary part. Okay, so it'll look a bit different. So we have y of x is equal to a e to the lambda 1x plus b e to the lambda 2x. Then we just substitute and simplify. So this will be a e to the, remember your brackets because we've got two parts here. So 3 over 2 plus I root 3 over 2. All of that times x plus b e to the same thing, 3 over 2. Sorry, minus this time. I root 3 over 2 times x. Okay, now you can leave it like this. It looks a bit complicated, so we're going to simplify. So we have a. We're going to take the real parts out as a separate term, e to the 3 over 2x. Okay, and then the imaginary part, we're going to make its own term. Plus, and then b, same thing. We're going to take the real part out as its own term. And the imaginary part as its own term. Okay, so why am I doing that? Well, because those two imaginary parts, we can just use Euler's formula. Okay, we can't use Euler's formula if there's a real part. Euler's formula only works with e to the I x or e to the r theta. Okay, so let's do that. So we have a e to the 3 over 2x. Okay, Euler's formula for the first one, that will be cos root 3 over 2x plus I sin root 3 over 2x. Okay, so that'll be for the first one. And then the second one, very similar, but we got that minus sign. Okay, minus I sin root 3 over 2x. Okay. Now, the e to the 3 over 2x, that's common to both. We can take that out. Okay, and what are we left with? Something times cos, so let's call it a new coefficient c. Plus some other complex number times sine. Okay. Any questions for this one? Yep. Yes. The I that goes with the B and the other one that goes with the A, I combine all of that into D. It's all inside D there. Yeah. But those could still be complex. We don't know. Yeah. But once you substitute your initial conditions or your boundary values, you'll get real numbers for that. Okay. Any questions? Oh, good. Okay, just a few notes. Your quiz 18, it was 18 you did? Okay, so that's marked. The solutions are up, your results are up. You can have a look at that. That will be the last of your formative assessments. So all of that's done now. So next week will be the catch-up for those that have missed anything. I have posted the list already, so just check if there's any mistakes there. Then next week, Tuesday, you got your catch-up. You should know who's doing that now. Then the week after, your class test. And then you're done with your class mark. Okay. Those with above 40%, I will see you at the exams. If you do not make DP, you have failed. Next year, you'll have to do Math 141. Okay. Any questions on that? Okay. If there are any issues next year when you're registering, just come see any of us, right? Dr. Chetty, Evans, or me. We can help you out with what you need to choose. Okay, because the major issue is if you fail the 161, you don't have enough credits to do the Math 238 next year. And I think there's a civil engineering module that you can't do. That gets blocked. Electrical engineering, I think that gets blocked by 142. So if you fail the 142, I think that also gets blocked. And then there was another math module, I can't remember, but we'll see next year when you register. Okay, any questions before we go? All good. Okay.